So I'm going to talk about Python perspective on OpenStack Swift, but I'll touch upon the Swift itself just in case I have people who are not familiar with that. Swift is an object server accessible over HTTP. So in many ways, it's similar to S3, although it's not identical. It has its own protocol, its own community of users and all that stuff. But they're broadly similar. And it's all written in Python. That's what brought me to this talk, because I talked to so many people who think that Python is interpreted language and therefore it has certain performance limitations that they have preconceived ideas about. And they're right to some extent. Like if you try to code something like some loops or move some data around, you will definitely lose to a language such as Go in that sort of head-to-head comparison. But when users compare or benchmark Swift against implementations such as Ceph or such, Swift sometimes wins, and well, pretty often actually. And just on the performance and how that happens, well, mostly because of the scalability. Just because Swift is tuned to support very large clusters, as soon as geographic distribution gets into play, it attains certain edge. It will lose within the same data center for Ceph. That's for sure. Okay, if you just have micro benchmarks, it will not be able to keep up. But as soon as your user start hammering the system, it goes ahead. So Swift overall is somewhat simple in its architecture. Well, this is a very simplified overview, but I think that's going to be sufficient for this talk. It has a two-layer architecture, although on this one you can see 3 layers. A load balancer is on front, but that is not part of Swift. We always put it into reference architectures because load balancers terminate SSL, and that is very essential. They have to do it safely and in a performant way, and sometimes this is hardware assisted. So Python starts in the second layer, where for us it's the first layer. So proxy is one layer, and the backend or storage is the other layer. So that's how it's all done. I think that's pretty easy to see or keep in mind when we talk about Swift, how it works. Client traffic comes through the proxy and reaches storage and then back. So it goes up and down. And there is replication traffic that goes across left to right, and it bypasses proxy. Most largest clusters have their own network for it, and it can be like a different technology, even such as InfiniBand. So before we go to Python, there was something I wanted to mention. Well, I already started, but things that we probably want to highlight about Swift, such as the proxy is called that because it hides the actual topology of the cluster and how it works to some extent as a proxy. This goes in balance with what I want to say next, which is layers are not completely isolated. So your request most of the time as a client, most of the time matches one-to-one to request in the backend. And most importantly, responses from the backend are visible. But this is done in such a way that you cannot infer topology. That helps your applications to be portable. And this contrast with Ceph, that in the service of performance allows you a visibility into the cluster. Not only allows, it's essential. Your client has to go to monitor, download the cluster map, and then use this information to to find your group leader to which you talk, and then you talk directly to OSD that hosts your object. That absolutely is beneficial to performance of that client at the expense of, lack of different trade-offs for the visibility and the portability of your application. So Swift does it differently, and of course that loads up proxy with the CPU consumption. Proxies absolutely are CPU intensive, and I forgot to mention that on the previous slide. When we talk about Swift, we usually keep in mind certain characteristics such as scale of Swift. So larger clusters implemented by telcos or large companies such as BMW and like companies like NVIDIA has a largest cluster, but they mostly use them to store artificial intelligence data. They have some sort of hosted artificial intelligence payload that use Swift as a backend storage. So for those clusters, proxies are not very numerous. I think it's unheard of to have more than 20. And actually even that is too many. Like of them have like 8 or 12. But they're like really big computers with powerful CPUs. And you have close to like 10 or up to 100 backend nodes. And this number used actually to be higher because you have thousands upon thousands of drives. But during the lifetime of Swift, nodes kept getting fatter and fatter. We can talk about this separately, but because it has nothing to do with Python, and it's just the way storage technology has evolved. So we used to build clusters from 1U nodes, and you stack them like pizzas. But now, like a rack is typically your node, and you have like a server, like a 4U server or something, and the rest of it are just drives, and you can have hundreds of drives per node. So that's what we're talking about here. So that's the hardware assumptions that are built into Swift. What else it has? It has a distributed hash table, which is the foundation of the distribution, and it allows basically maps names of objects to like your node number and device name and some identifier that is used to basically turns into a file name and the backing file system. I think maybe like in some other context I could talk at length about how amazing that is, and I thought that was something that drew me to Swift as an implementation as I learned how it was working. So one of interesting part of Swift is that it's very different in its nature to most other storage systems that try to implement consistency as the first priority. They needed to support block storage and back VMs and stuff like that. And Swift doesn't do anything like this, so it disposes with the consistency. Strongly consistent storage systems, again, Ceph is a good example, usually have voting and they have leaders, and they this is the foundation. And in Swift, you don't have any of that. It's much simpler. It has these static files that are read from disk into processes, into worker processes. And those files contain cluster map, essentially, and the foundations for the hash table for each of the layers. Beyond that, I already mentioned that Swift has a bunch of replicators that do most of the heavy lifting for maintaining cluster health. They also delete old objects and stuff like that. And you have a bunch of other auxiliary processes that I omitted from my diagram just for simplicity. All right, I think I talked enough of that. Let's go. About Python. So Swift is written in Python, and one of the guiding approaches for this was actually simplicity. Simplicity of the first implementation of MVP that you have to have, And after that, even though it grew in size tremendously over the years, uh, so I have my concern that newcomers to Swift would be able to keep this, navigate the code. It's just too big. But we still strive to be as simple as possible. And for example, if we look at our multiprocessing model, it doesn't have anything particularly fancy. You just have a fork, and you create this worker processes, and then you have worker process, and then you have a bunch of threads. We're going to talk about this. Swift is implemented with eventlet, although there was some effort to port it to some other implementations. It can run under Apache, but eventlet is the first and foremost, if not the only one, the only way to run Swift. And eventlet is a library that provides greening, essentially implements green threads, and it provides a web server. Well, I guess everyone in the Python meetup understands what monkey patching is. And in order to have your threads green, eventlet extensively monkey patches. We're going to talk about it in a minute. Visgy is also something some of you may know, although I'm not sure. It's what it is, an interface between the web server and the Python application. Visgy is a Python thing. It includes various features in itself, like the server itself, the API for it, but also a thing called a pipeline where application can have filters, and those filters are called middleware. I'm sorry I'm mentioning this in such details, but I remember I went to like a summit and people were talking middleware this, middleware that, and it completely screwed up with my understanding of what was going on. But middleware is basically a function that you can call, and then it calls exactly the same function, and they're all chained together until it hits the end of the pipeline, which is your application. So that's all. And then you do the same thing when you unwind that stack. That's all middleware is. Swift also relies on things such as web objects, but and that was part of the evolution. When Swift started, it used a fairly normal web ob, but then we implemented it anew. The main reason was that we needed more stable API for that. And then I'll mention the HTTP client, and which we also, but did not re-implement, but rather augmented. And rsync, which is the backend transfer technology for replicators. And also Python 3 and all that other stuff. That was fun in a bad way. I'm going to rant about it if anyone is interested and if we have time. But Python 3 took a lot of effort. It literally took two of us a year, like solid year, just converting to Python 3. You would think it, well, anyway, whatever. It was just terrible. But it works now. Everything is fine. It's all on Python 3. Also, as another example of evolution of Swift, we disposed with pickles, which were primarily insecure. People always kept finding vectors to attack pickles with some sort of garbage. You load into them, and we replaced them with JSON. It's much easier. JSON is not as dangerous. Another thing with pickles is that you can crash your servers just by reading bad pickle. And that is not necessarily malicious. It can be just a bad file. Even these days, when all the blocks on all the drives are covered with ECCs and the drives are flash drives, you still find bad bits. At the scale at which Swift operates, this is literally like daily occurrence. You wouldn't like. I sometimes wonder how that can happen, because the math of it doesn't add up. CRCs are just long enough, like distances in that coding are long enough that shouldn't be happening, but we absolutely see bad bits on the storage. Maybe bugs in your drive firmware. So let's start with fork. Oops. As I said, this is like almost too trivial for this esteemed meetup, but I'll just mention it anyway because this is the foundation of Swift performance. Be simple, don't do anything excessive, and the most interesting part here, I think, is this. Oops. Oh, brother. I forgot that I'm in presentation and double-clicked on it. We use pipes as an intercommunication mechanism, and that turned out to be the best for our purposes. It's simple and always works bug-free. One other thing that you mentioned at you notice at scale is that bugs always float up. You can have something absolutely impossible, almost, like extremely rare condition, and it would always happen. Just like those bad beats on your drives. You wouldn't think it's possible. Swift always finds some sort of a bug in library, and that is one of the reasons why we do this. In computer science courses, it's the first thing you're being taught is just not invent a bicycle, because you will never outcompete properly written library function. But unfortunately, in this case, at the Swift scale, we keep like struggling with this. Well, not struggling, but fighting. So that's why we have this absolutely trivial code, and this is actually copied from our server. That what they literally run. They do this fork, and then, well, we'll look at the run server in the next slide. So you just invoke a function, right? Scalability is also very trivial for this. We just fork to consume all the CPU, and then you have a pool that's large enough to sustain your requests inside the pool of green thread. Okay. So eventlet. This is one of the most Pythonic things of. Well, I don't know. It's such a fun project, and firstly, the way it uses monkey patching is just absolutely out of control. You don't see anything like this unless you run unit tests or something like this. But it has to do it just so that you can do your threading. So firstly, eventlet is flexible. So the first thing you do is switch so-called hub. It has several implementations, and the simpler one uses select. They also have a poll and epoll, and I really hope for your ring coming online, but not sure. And epoll is faster than poll, but we use poll because epoll has these annoying hangs in it. We are not exactly sure why that is happening, but it's just the difference in performance is not sufficient to fight it. So we just use poll. It's all configurable, of course. But also, when you initialize the eventlet, you have to screw around with things like substitute logs from eventlet, because you could hope that it greens it properly, but it does not necessarily do it. So it's easier to do it this way. And then this is the run server that we saw in the previous slide, and it goes like this: call eventlet to patch, and it does it explicitly. The advantage of that is that it's easier to configure. Not all of our servers do exactly the same monkey patching. Well, this is stolen from the proxy, which has to monkey patch almost everything. Socket and select is inter-process communication inside eventlet, and threading is also green. So, there is this bullet. Just ignore it. I forgot to delete it. So this is a continuation of the run server. Next thing you call load app to create an app. And an app is your main class for your WSGI. So that has some methods that server invokes, and you basically initialize all of that step by step, and you call WSGI.server, and that's it. Now you have the server. It's gonna listen for you, do everything. Yeah. So moving forward. So this is what WSGI is. Please pardon me if this is too trivial for you, but I'm just going to mention it real quick. So this is the application that I mentioned. And it runs like this. You have some initialization that is invoked when load app brings it up. All right. So by the way, you don't have to use paste deploy. Load up comes from paste deploy, but of course you can construct application class by hand if you want. Only the class itself is a part of the 333 PEP. So you construct a class, initialize it, and then you feed it into the eventlet. And eventlet just called it, and you make it callable. And the call has this particular signature, which is defined in the PEP. And then you do your thing, create a request. Request is the webob. And then, do whatever you want with that request. Like accept some input, read files and whatever, and then call some other services. And then the return of that request is just a bunch of bytes that WSGI server feeds into the client over HTTP. So this is a very simple basic structure, and as you read Swift, what's kind of, I already talked about it. It's just very big, but that's how it's supposed to look to you. You read and mentally just skip all this stuff, and you know that these calls are essential, and all the rest of it is just like checking various permissions, error conditions, all that stuff. So, but the structure is not the only way WSGI affects Swift, and I really want to say unfortunately, because another thing WSGI kind of puts on us is the way it encodes headers in Python 3. In Python 3, and well, the magic here is this WSGI to str thing, and it goes to your webob, gets whatever it is, and that thing is in WSGI encoding. And WSGI encoding is identity encoded to Latin. It uses strings which are Unicode, but they're encoded in Latin 1. So actually, they look like strings, but they contain bytes inside. So in order to do anything with that string, you have to convert it to something. In this case, it's WSGI to string. It converts it into normal string. And that conversion is implemented by WSGI to bytes first, which is a Latin 1 identity encoding, and then decode to with the UTF-8. So and the end result is something that you can look at. So this stuff is everywhere, and the unfortunate side effect of it is that like everyone in this group understands that Python has introspection. So you can look at an object and know that this is a string, not like 4 bytes, right? And this is very convenient, and you can use it with existence or some other way. Well, unfortunately, with WSGI that doesn't work because you have the same string and you cannot tell if it bytes or not. It may be identity encoding or maybe not. That I don't want to say that it was like a big mistake, because PEP authors had a reason to do it this way, but it's so hard to work with. You cannot rely on typing. You have to do it. And we did the conversion before MyPy became as prevalent as it is now. So we didn't have a MyPy at all in Swift. So you don't have any types. You have to really look at every variable and know which type it is, either WSGI or string. That unfortunately added a lot of workload to managing it. So yeah, good and bad, but mostly good. I think oh yeah, another thing about WSGI is that if you look at PEP, the very first thing it says, please don't write apps to WSGI ever. You have so many good frameworks like Django or whatever. You write your apps to them, and WSGI is only there to serve as a glue to your web server, so that you can be portable. So that authors of web servers know how to do it. But Swift immediately violates them. Says like, we are written to WSGI. That is mostly for performance reasons. We would love to use a framework if there was a fast enough one. So yeah. WebOb is somewhat different. Yeah, I'll look at the chat later in the recording. WebOb is that thing that has a class request, and we forked it primarily because WebOb itself was not stable enough, and not stable enough meaning not compatible, not backwards compatible enough. So there were issues of that nature. And once we did that, well, of course, we could modify it to suit. And some of that stuff is this how it helps handling the WSGI specifically. WebOb itself doesn't care about it, but Swift WebOb, which is called SWOB does. SWOB includes these things like various header helpers, such as this one, and you can see how it decodes Latin 1 if it's, well, let me see if it does. I copy pasted it from somewhere just to give you a taste of all that stuff, but I'm not exactly sure if this is correct. No, it should be. Yeah. So this is the Swift WebOb, and I think it's justified. I was kind of nervous when this was proposed, and because if we start forking everything, like, why don't we rewrite Linux, right? Like, where do we stop? But in this case, I think it was justified, and it's useful code. I hope it helps someone one day beyond just users of Swift. HTTP client was different. We didn't fork it. Instead, we augmented, and I think I copied this part primarily for the comment that says that yeah, it would be great if it worked this way, but it does not. So we added this thing, and at least at the time, Python standard library would read HTTP just byte after byte, which is okay for headers, but once you start pushing bulk around, remember the proxies are always CPU bound. That would actually float in the profiler. You can see that the way standard library does it was not sustainable for us. So that's where these implementations come about, and it's not that complicated. It's just bufferized read. That's all. Well, I lie, of course. Every time you create something like this, you find some things to hang on it, and you have like a whole bunch of auxiliary code that does this and that. But turned out to be okay. It's not very troublesome to maintain, even in Python 3. For the rsync, there is not much to say. It's just that, rsync is written in C, so it's faster. And well, it helps to have it faster, and also saved a lot of effort because rsync renames files properly, and that has this it turned out to be very robust and free of bugs, which was a big help. So I guess the lesson here is that I don't have to like even search for a library. If you can do it in such a way that a binary does it for you, well, just do this. We literally have p open in those replicators. Swift actually had has its own replication protocol. It's not just syncing things around. Don't misunderstand. It has support for rsync, where it sends hashes of objects that are combined into dictionaries, and then it can compare those hashes and see which objects need syncing, and that's how you form the lists and for the job, for every rsync job. And also databases are synced record by record, essentially. You have sync points and or double sync points when one of them goes up and another catches up. That's how databases are synced. So, but they can be rsync if you have a new node brought online. It's more efficient just to jam the whole database over rather than go record by record. So that's about all I wanted to say in Python, and I think the overriding thing here is the simplicity of it. I'm just have this big concern that people would read Swift's code, and then they would not see it as simple. It's just big. But in reality, well, not in reality, but in my mind, it's this kind of simple underlying architecture on which you can play and create complicated things. It has things, for example, like erasure coding, which is absolutely, but basically a real erasure coding, not just some toy. Also, Swift has things like container sharding, which is stupidly complicated. I completely omitted it here because firstly, it tells us nothing about Python, and also it's too hard. You can spend hours talking about it. But that's the impression I wanted to leave about Swift. If anyone have any questions, I would be happy to answer. Otherwise, please visit the source code. And oh yeah, the Swift container. Is it okay if I answer it right now?
Yeah, go ahead.
Swift container is a bucket in terms of S3. And Swift has this really nasty habit of reusing names in ways with which I disagree, which are not conventional. For example, one of the most important things in the hash is called partition. And partition is actually has nothing to do with disk partition. It's a segment of hash space, basically. That's what it is. So it's kind of virtual, but it also corresponds to a directory in the backing file system. It's implemented as a directory, right? So so you have a partition that, and like people keep getting confused about this all the time. Container is another example. So Swift's container is either bucket or directory, however you want to call it. But we call it container. I don't know why. Although Swift originated before the containerization, but Linux containers existed, they just weren't pervasive. So why did they call it container? Well, another thing is Linux is Swift device. Now that one is more justified because it's often maps to a device, but it's not actually a device. It's a mount point. And finally, sharding has a thing called namespace, which is not a namespace. It's just a shard. Like, well, they renamed it namespace because it doesn't correspond to one shard. It's a section of object names that are lexicographically near each other. So yeah, dealing with Swift, you have to deal with, oh yeah, proxy. Proxy is also a thing. Like, so every time I write something, some email, I force myself to write Swift proxy, Swift container, Swift device, because otherwise it's really confusing. And I'm sorry about this, but I was not the one who created it. I hope that answers it.
That's cool. Yeah.
I have a question. So I understand that it's a way, Swift is a way to actually make use of much more space than you actually have. But can you give specific applications of how it's actually being used? Some examples of real applications that people use Swift.
Yeah, and I do have a question. Yes, I do have a question like similar to that, almost the same. It's like, what would be like the minimum hardware requirements to like for somebody to play with this?
Well, let's see. Well, I have a laptop here that runs a minimum Swift, and that's just a single node that I use for testing. It actually has a what's inside the container. I use it for work. I have to work on backup or OpenStack. Oh, that's a bunch of backups. Yeah, a bunch of segments. So you can use it in this way, but that's completely overkill for the task. Obviously,
something is wrong with the audio. Something has changed. Can you repeat what you just said? So, and then, like you,
Yeah,
I don't.
Yeah.
No, audio is still bad. You might have an echo or something. Now we can't hear you.
It's probably internet connection because it's like breaking up. Yeah, some kind of a robot voices there.
Yeah. No, it's like an echo. Something got lost.
well,
Okay.
How about now? Is it better?
Now it's okay. Now it's okay. Please talk.
All right. Well, this connection is wired, so maybe that helps. I don't know. The previous one was Wi-Fi. So we have a question about size of Swift, and although, as you can see, Swift can be used in a single node, it's too heavy for that. You have something like 20-30 processes running around and doing stuff. You have auditors that constantly audit. That is, by the way, a source of contention with some people. And we always laugh at Gluster people, where in order to understand that your file is bad, you have to read it explicitly. In Swift, that happens behind your back. You don't have to worry about that. So I would say that smallest practical cluster that I saw, I think, was something like 4 nodes, and I'm saying like hardware, and they were all what we call PACO, PACO, so account, container, object, and proxy. They're all the same. So you have 4 proxies and 4 backend nodes, and that was used by Ministry of Sport of Brazil to store their soccer players and their, well, it's a very big secret and state secret anyway. So basically storing this sort of information. You obviously you don't have that many footballers even in Brazil. Well, maybe 1,000. I don't know like how many they actually have there. So so you don't really need Swift for that. They only needed Swift for durability of the data. They could not afford to lose it. So you can accomplish it other ways, like have someone store the your biographies of your football players on optical disk and send it by airplane to another city. You know, still would provide the durability, but they chose Swift for geographic distribution. As far as the biggest cluster that I saw, they were on the numbers that I mentioned, where you have something like, I want to say, pushing a petabyte, and you have thousands of disk drives. And even now, people still use rotating storage just because it's cheaper at this sort of scale. I can't wait for Flash to catch up. I believe that it will. So as far as applications, I think one of the first ones that kind of I still remember and I can talk about is mobile gaming. That's where service providers and game developers, primarily, they allow direct access to Swift for performance. And then they load things like, I don't want to say game maps, but usually assets of some sort. And also your per player assets, which in countries like Korea and Japan easily can reach 40 million per cluster. And just because their telcos are just freaking monopolies and they have like 5 telcos per country or even less than that, and everyone on that particular provider plays one game that is popular. Yeah, I don't know. That's just the way they were at the time. And then everyone can upload their own photo, and that photo is in Swift, so that it's an avatar. So that's a common application. Another thing that people like to store in Swift is logs, primarily by various devices, and that can be, I want to say, refrigerators or stuff like that. So I hope that gives you an idea and what people do with Swift. Oh yeah, let's talk about something else. There are things that Swift cannot do. Like, for example, if you have virtual machines, no matter how, and you have like tens of thousands of them, you cannot back them by Swift. Swift does not have enough consistency to support block device. It's, well, it actually kind of does, but you know, Swift is eventually consistent. But if you like write objects in it, and then Swift gives you 201, then you may be sure that it's there. If you read again, you will definitely hit that object and you will read the data that you've written. You will not read the stale data from that object. Even for intercontinental clusters. So, but your read can be delayed while this thing appears, while your write is still being propagated. But unfortunately, things like containers, they take a while to sync them. So that's why the virtual consistency. But this is enough for it being useless for backing your VMs.
So you can see like things that are not that, they are often found in Swift.
So you're saying these clusters could be like on different data centers. So you can have like one cluster, but it can be like distributed on different data centers, or is
No, we usually distribute one cluster. Don't federate.
Okay.
So you have one cluster and you have some proxies on one place and some on the other place.
okay?
And you have some affinity, but it's the same cluster, so it usually has the same authenticator. Well, technically, you don't have to. So you can have half of them authenticate in their own data center, and half of them authenticate in another data center. And as long as your users are consistent, the client will never notice.
Got it. Cool.
But Swift and Ceph absolutely are. Yeah. Ceph is one of those classical, well, both of them are DHTs, right? So that's a comparison right there. So, but Ceph is completely different in its approach. It has these elections everywhere. Everything, like you have elections, like every little thing in Ceph is subject to elections, and you select a leader. They partition everything, like where your object is stored. They store them in these, I want to say allocation groups. I forgot what it's called, but basically these group things where you have 3 or 4 OSDs for each of the sections of the address space, and then one of them is always a leader, and they have very robust infrastructure that maintains integrity of all this thing, provides elections, provides updates, and the leader is responsible for the replication within the group, right? So it's always strongly consistent. So the end result of it is that Ceph can be faster than Swift significantly within a data center. Just because you don't have a proxy, you talk to OSD, so you can fetch immediately, store immediately. They only become comparable in speed when geographic replication isn't when it's between continents, essentially, right? So in fact, Ceph disposes with its strong consistency and uses asynchronous replication because otherwise your response time becomes untenable. So it becomes kind of similar like Swift, and it has a separate layer that works almost like Swift, but Swift doesn't have anything else. It only has that layer, right? And it doesn't have leaders or anything like this. It's much simpler in its design, and it's more static. So it has good and bad. Like Ceph implements, so basically it has this Rados, that's an objects layer, right? And it has these 3 pillars. Well, not pillars. 3 they're backwards, right? Not pillars, but 3 main thing. 3 main users: RGW, which implements S3 and Swift. So you can Swift applications running against Ceph. What's the second? Oh yeah, RBD, which is the block storage. It allows you to back your VMs. And CephFS, which is a POSIX compatible file system. And if you look at this, RGW and Swift are literally the same, but there is no CephFS equivalent in Swift and no equivalent for RBD. So Ceph has these functions that are not present. So there can be no competition. It always wins. If you want to have a POSIX file system, Ceph wins, right? Distributed for POSIX file system, right? If we talk about RGW, well, that is more complicated. And well, RGW has native S3, so its internal structure is kind of more like S3. So it's better at emulating S3. Swift is worse. However, well, for example, consider this: RGW is user of Redis, and it needs and Redis, and they talk to Redis not by HTTP but by Ceph, and that means that primitives it uses are like things like blocks and but basically these objects, and the way it maps all the indexes are also objects like this. So whenever RGW wants to update your bucket contents, and it has to, like on every write, it has to go into Redis, fetch this, modify it, write it again. There are some complications. Because of this, its performance would be like very bad. So it uses loadable objects that are parts of RGW that are executed on your OSD, close to the storage, right? And the protocol between them is RPC. And the downside of that is that you cannot update Ceph cluster without downtime. In Swift, you can. You can have clusters that literally have zero downtime, not just 999. Well, they have 999, but primarily because of the load balancer. But Swift itself is zero downtime system, which is very attractive to service providers, to cell phone companies primarily. They just don't have scheduled downtime at all. Your cell phone always works, right? So so that's a point of comparison between Swift and RGW. So yeah, absolutely you can compare them. And Ceph is a really good system. I spent like some time working on Ceph here and there, and you can like grab their logos to see what I did for Ceph, but it was not much at all. But it's an interesting system. I enjoyed working on it. Do we have anything else?
All right, any more questions? Going once, going twice. All right, thank you, Pete. It was an awesome talk.
Make some noise.
Yeah,
Yeah.
thank you.